Thank you, Tony. It's amazing to think of a company founded in April of this year, and in 2.5 months, they've actually got cars out in the streets that are driving on their own. Speaks to the amazing amount of progress we've made and the ability to leverage machine learning to get going. Our next speaker is Danny Shapiro, who is Senior Director of Automotive at NVIDIA, where he's been for the last 9 years. NVIDIA, as you guys know, is a leading chip maker and technology provider within the automotive space. And Danny actually manages partnerships with over 200 different partners in the automotive space. Danny, please join us here.
Thanks so much. Good afternoon, everyone. It's really nice to be here, and what an amazing conference. I think the sessions that have been going on all day are really showing how widespread artificial intelligence and deep learning are, and really kind of what the future is going to hold for us. By show of hands, how many of you grew up playing video games? Pretty much everybody, right? And so, and you probably know NVIDIA. You think of NVIDIA as the graphics company. And that's something that we still do. And again, you're looking at all these really cool graphics. And again, NVIDIA is kind of rooted in that and parallel processing. And of course, we've made a shift and really reinvented ourselves and are now really the AI computing company. We still do the graphics, but AI is really fundamentally changing every industry. So if we look at kind of across the spectrum, whether it's in high performance computing, whether it's in internet service providers, Amazon and Google and Baidu, cars we'll come back to, but even like medicine. High performance computing and AI are transforming all of these industries. On the trucking, logistics, warehousing, again, these are all big data problems, and we're able to train these systems to become better than humans to be able to perform these specific tasks. But I guess we just want to focus for today on autonomous vehicles. And really what we're seeing, though, is a combination of training that has to, of course, take place in the data center, but the key is being able to do real-time inference at the edge on the devices. And so we build these neural net models, as we've talked about, and then they're being deployed in devices, whether it's everything from your phone to watches to cameras, and all different kinds of autonomous machines. Literally, there's going to be billions of AI-enabled devices at the edge, but we're still looking at a huge market opportunity of probably hundreds of millions of autonomous machines, all types of robots with wheels and other types of traction on the roads and being used elsewhere, as Jeff already showed some examples of. So as we look at this whole spectrum, what we've basically been able to develop, and we're providing the tools for all of you to develop your neural nets, to be able to test, as we saw in some of the sessions earlier today, run your training sets, iterate on that, and doing this everywhere from the data center all the way to the edge, including all these different autonomous machines. All right, so let's really, though, focus on the autonomous vehicles. I think you've gotten a really basic and good understanding of the complexity of what's happening here, and also what's at stake. It is so serious what we're doing. This is not a recommendation engine for Netflix or Amazon, right? If the AI is pretty good and you don't get the best recommendation, it's not a big deal. But now we're driving high speed. The AI has to be spot on. It cannot make mistakes. And so it requires a tremendous amount of computing. And as you've seen, a lot of code. We each seem to have our own kind of block diagrams. And again, robotics, it's a fairly well understood problem. There's just a lot of different ways to approach that problem. And so what we've done here, though, is again, build a whole platform and a software stack to enable others to make their vehicles. So NVIDIA has our Drive PX is our car computer. It's an AI computer designed specifically for vehicles. And on top of that, we develop a Drive operating system. We have a variety of SDKs for developers, for the car makers, for the tier ones. Our Drive AV stack is the autonomous vehicle code, so it's neural networks for detection of lanes, of objects, for open road processing. And then the ability to take all these different inputs. So this product takes in camera data from up to 12 cameras, radar, LiDAR, ultrasonics, HD maps, and even vehicle-to-vehicle or vehicle-to-infrastructure communication, and uses that to be able to create this whole environment model, modeling everything that's happening around the vehicle. Now, ironically, it kind of starts to look like video games, right? As we build this virtual world that mirrors the real world, right, we're able to leverage a lot of that graphics technology and horsepower and 3D modeling to be able to create this in real time in a fraction of a second. 1/30th of a second. We need to be able to scan everything, understand what's going on, and then be able to make a decision before the next set of data comes in 1/30th of a second later. What I want to do here is show you a video of some of the development stuff that we've been working on. And again, this platform goes into the car. It can go into the car as a PC with a bunch of NVIDIA GPUs, or here you can see a picture of one of our Drive PXs. So it's small, fit in your hand, much smaller than a PC, of course. And here we're able to run all these different neural nets, whether it's perceiving objects in night, in day, in different weather, being able to get data from the different sensors. Again, key thing being able to understand exactly the distance to different objects and the speed. On the bottom here, you can see then how the deep neural networks are interpreting the video environment. We have systems of stitching cameras together. This vehicle has 6 cameras around it, and so we're able to do 360-degree detection of objects. So again, these cars become superhuman in terms of their performance, in terms of their perception, and the capability of tracking everything. As a human driver, you have very limited field of view. We're also running, again, a whole variety of different neural nets. Here we're understanding the free space. Where can a car drive without hitting anything? And we combine that with object detection. So we have basically redundancy of different types of algorithms to ensure that we're able to track what we want to avoid and know where we can drive safely. Again, all these steps, the pipeline, require a massive amount of compute performance. Cameras are getting higher resolution, the LiDAR is having more lines of resolution, more radar. It all generates massive amounts of data. And so what we find is that just more and more and more compute required to actually make the decisions to safely drive the vehicle. And we're not stopping. Like in any form of computer science and now data science, the level of complexity of the software keeps increasing, right? We keep adding more layers, more algorithms. The more data we have, the more diverse algorithms we have, the safer these vehicles are going to be. And then we need to be able to test them on real roads. And so what we're doing is, again, combining a whole variety of different technologies to be able to put a car on the road. So this is BB-8. This is one of our test vehicles. We're not obviously making cars, but we feel we need to understand the entire pipeline of everything to enable companies to build robo-taxis. This is the ultimate goal, right? Goldman Sachs did a study, and they're estimating almost $300 billion in terms of the market size in 2030. So again, you have all these companies and more, right, that are out there developing technology, and the reality is we're working with virtually all of them. What's different, we heard a little bit about the different levels of technology. Level 2 is, again, some basic driver assistance, and you're seeing more and more cameras, radar, and even in some cases LiDAR. Audi just announced the first level 3 car will go on sale later this year in Germany and then come to the US. Level 3 means the driver can take their hands off the wheel, their feet off the pedals, and the car is going to drive itself in certain situations. But how great would that be out here on 101 in traffic? You don't have to do anything. You're freed up to have that time back in your day. So NVIDIA has been working with Audi to develop this system that is this traffic jam assist or traffic jam pilot. But that's not enough to get to level 5. For level 5, as you've seen earlier, these vehicles have a vast array of cameras, of sensors, LiDAR, radar. They have to be able to track everything. And so to do that, this is kind of what it looks like in many vehicles. This is actually from Ford's car. They have a self-driving program. They have a fleet of about 30 or 40 cars. And this is what the trunk looks like. On the left side, that white box is essentially a very powerful PC. And in it are a couple of NVIDIA GPUs that are doing all of the deep learning. They're figuring out all that data that's coming in that is basically just ones and zeros, but using deep learning to figure out what's a car, what's a truck, what's a pedestrian, what's a fire hydrant, and the list goes on. What we realized is, of course, there's no way that you can put this into production. It's great for prototyping, but to actually go into production vehicles, we need a better solution. So a couple weeks ago, we introduced the new version of our Drive PX called Pegasus. This is the size of it. It's about the size of a license plate. Our current product that's being used for development, it's in Tesla. It's been in the Tesla for a year now for autopilot. That's rated at about 24 trillion operations per second, or 24 tops. With Pegasus now, we've increased that by over a factor of 10, 320 tops. So this is a supercomputer in the trunk that now, again, all of you who are working on self-driving cars, the panelists that we're working with, those kinds of companies are able to now have a path to production to bring these products to market. The other thing that I want to show you is work we're doing inside the car. So AI can be applied not to sensors outside the car, but if we have a front-facing camera, we can identify who's in the vehicle. We can watch and track their eye positions. We can know where they're looking. Are they falling asleep? Are they distracted? This is critical information. What we can do is actually offer a lot of features within vehicles that will make both the passengers and driver of the vehicle safer, as well as people around the vehicle. So for example, if you're at a stoplight and you're wanting to make a right turn, you're often looking over to your left. But if someone were to step off the curb and you're not paying attention, this system will enable the vehicle to alert the driver to something that they might not see. We can also do lip reading. So there's a whole variety of different in-vehicle tasks. We can, again, merge things from outside the vehicle.
Careful, there is a motorcycle approaching the center lane.
And inside the vehicle. So giving you the ability to find stuff that you didn't otherwise notice. And in this example, driver comes up to the red light, waiting for it to turn green. It turns green. She's about to go.
Cross traffic danger.
But our system detected someone running a red light, and it prevented her from going out into the intersection. So again, there's going to be a whole host of new guardian angel type of features. Even if we're not fully self-driving, we can use AI in the car and outside the car to make everyone a lot safer. And so we call this Drive iX. This is our intelligent experience software development kit. Again, what we're doing are building the tools, the building blocks, the hardware, the software, all these layers that we make available to the ecosystem. We're working with over 225 different companies who are building autonomous vehicles. So from the car makers, the car sharing companies, the tier ones, the mapping companies, startups, the list goes on and on. Everyone is getting involved in this, but they don't have to start from scratch. And so they're able to build on this platform and all these different software layers that can then enable really cool kinds of apps in the car. You know, as you park the car and you're about to get out, there's software that's checking to see, is a bicyclist coming up or a motorcycle, and will caution you from opening the door and causing an accident. So again, I think what we want to see over the future is going to be a great user experience. Our focus is on safety. I know we're working with many companies who share that same goal. How do we increase productivity for the time that we have to be in the car? How do we improve traffic, meaning reduce the congestion or make people more efficient behind the wheel? And also, of course, that those accident numbers that we heard at the very beginning of the session, they're going up, they're going in the wrong direction. As we can put more and more of this technology in cars and trucks and all kinds of vehicles, we're going to have much safer roads. Thank you very much. So I think at this point I'll invite my co-speakers and panelists and moderator back up on the stage. Maybe we'll invite you guys up to bring some chairs too.